Good evening, everyone. Today is the eighth week of the microwave remote sensing and hydrology. So, in the last week, we discussed about the classification. It is the basic classification in remote sensing that we study, and we also studied about basics of supervised classification and unsupervised classification. What does that mean? And today, I will cover some part of unsupervised classification, some theoretical part, and then I will start one totally new domain in SAR, that is called INSAR or interferometry SAR. So it will be the basics today. There will be no hands-on or practical exercise because those I will start from the next week after completing the theories. Today we will discuss one approach, very famous approach of unsupervised classification. We already saw that supervised classification and maximum likelihood classifier, how to do that in SNAP software, and how to collect the training data, and where we need training data or samples, where we don't need. So all those things and their advantages and disadvantages and limitations we already studied in the last week. Today we'll be discussing in detail about the unsupervised classification and its overall 2-3 points to know before starting. Many times unsupervised classification are preferred over the supervised classification because supervised classification, as we knew, that it is very much data dependent. That means the training samples dependent, and also that's how we, many times it depends on the analyst or the user that who is doing, and depends on his or her efficiency and the quality of the training samples. So many times in terms of, if you say, in hydrological applications using microwave data, unsupervised classification is still popular, and many are using or and proving in research that this unsupervised classification works better in every way, not only in accuracy, in terms of resources, in terms of time constraint, all other things. So it is very important to know what is unsupervised classification, and also one method we'll discuss. So again, it requires only minimal amount of initial input from the analyst. So minimal amount of initial input, it does not require that many, it does not require that many of training samples or any training samples, only your data. And it is a process whereby numerical operations are performed that search for natural groupings of the spectral properties of pixels examined in multipixel feature space. The user allows the computer to select the class means and covariance matrices to be used in the classification. Once the data are classified, the analyst attempts to assign these natural or spectral classes to the information classes of interest. This may not be easy. Some of the clusters may be meaningless as they represent mixed classes of Earth surface materials. This ambiguity is resolved by the analyst, who understands the spectral characteristics of the terrain in order to classify clusters into information classes. So obviously, both the classification approach, unsupervised and supervised classification approach, both depends on the analyst, but the dependency varies, and dependency domain is different. So in unsupervised classification also, it is all about experience, and after the classification it is about the post processing, which class to select, which class to not, or we need reiteration or not, all those things. and also it is based on totally mathematical approach, and both based on mathematical approach. But unsupervised classification, it works on some clustering approach or grouping approach. So we'll see that what mathematics behind. So clustering or grouping is one of the most important tasks in data mining and knowledge discovery. It attempts to find subsets within a given data that are similar enough to warrant further analysis. It organizes a set of objects into groups or clusters such that objects in the same group are similar to each other and different from those in other groups. These groups or clusters should have meaning in the context of a particular problem. So very important lines to focus. Clustering, okay, we are grouping something, some set of data based on some mathematical operations, based on their characteristics and behavior. Now, it by this approach or this method, we are basically collecting some set of groups. It depends. We also, it depends. We decide on the how many number of groups or clusters we want to classify the, suppose for our case, the image into. And one thing to understand, it is not only classifying into groups, it is also that one thing to keep in mind that each group are distinct from each other. It should not be like that two or multiple groups have similar properties and we are clustering separately. It should not be like that, so that we can classify further. We can tell, okay, these belong to class 1, suppose, these belong to class 2, suppose, but class 1 and class 2 should have enough discriminative property, you can say, in some way, and that depends on our task and our domain. If we consider in hydrology, suppose in flood detection, flood monitoring, mapping, that way we suppose we are making clusters of different flood pixels, then we should keep in mind and we should consider the properties that way that every clusters depict some distinctive properties of the flood. So these groups or clusters should have meaning in the context of a particular problem. So when mapping flood, it is different. When mapping suppose drought, it will be different. So it totally depends on our task, and we have to decide the discrimination, how to discriminate those groupings and clusters or those pixels to get the minimum and get a balance of the clusters. In clustering, one of important and fundamental tasks is the definition of proximity. Now we will go into the mathematics behind, and for the mathematics it is nothing but it is just we can visualize. So we need to understand proximity or similarity function between two data objects and the overall optimization search strategy, that is how to find the best overall grouping according to an optimization criteria. How the clustering process. So clustering, commonly known as unsupervised classification, does not need any training data, and it's especially useful when the user has limited knowledge about the data. So limited knowledge about the data, and as I told before that many times we prefer this, and it is proven that it gives very good accuracy over supervised classification if not handled that way, the supervised classification methods. Because suppose in flood detection, it is seen that when using unsupervised classification, suppose clustering method, so there we will not miss any flood pixels compared to supervised classification. That means, these practical applications, this has the that much importance in disaster response and mitigation, these things, hazard mapping. So there, to miss a flood area, it cost a lot. If you miss a flood area, that will hit in somewhere else, and it will cost, it will, I mean, it will be very not preferable case. So that way, how unsupervised classification, when you have definitely not that much knowledge and that much control over your model, your classification model, then it is better to use the clustering method, and with detailing, so that you will not miss any flood pixel that can be a flood. So this is why clustering is very much preferred in research also. Now clustering algorithms partition data into a certain number of clusters, groups, subsets or categories. There is no universally agreed upon definition. Of course, it depends on data to data, depends on your task. Most researchers describe a cluster by considering the internal homogeneity and the external separation. That is, patterns in the same cluster should be similar to each other, while patterns in different clusters should not. So they will try to find some pattern in our image. Both similarity and dissimilarity should be examinable in a clear and meaningful way. So one thing to understand, that in SAR image, as we saw the grayscale image, if you recall any of the image, those are very much, influenced by noise and speckle. You will not, definitely no one can say that okay, this pixel is so bright and this belongs to this class, this belongs to that class. It is complex SAR image, and their character, their similarity and pattern, to get a pattern from noisy image, it is difficult. So, but obviously it needs some experience handling to get the classification. So we need to find the homogeneity and the some factor, some pattern. So the process of clustering can be explained by 4 basic operations. First is feature selection or extraction, clustering algorithm design, cluster validation, and result interpretation. Because every classification, it needs the validation. It is meaningless without any validation with the ground truth. And result interpretation. Finally, we will interpret the result. So what we collect, suppose in the first, some data samples, suppose some SAR data we collect, SAR image. We form some SAR. Then feature selection or extraction. Feature selection, in the sense, this is not the, it is unsupervised, but we need to focus on some area as per our task. So if you are into flood mapping, then you will go, or you will select those areas of possible flooded areas that you want to classify. And that also, it is a task, it is a part, it is not data collection, because there many things depend. If suppose you are into the task is flood detection, then based on many other parameters you will decide your area, or you will select, then you will select your area. Similarly, for like for flood, suppose for riverine flood, you will see that distance from river, and also some other gauge station, rain gauge station, depends on those data. You will decide the as much as accuracy and efficiency you can get. So based on those, you will decide on your area. And the same task, suppose your task is in some other application, suppose drought detection or some other application, some other detection, then those there the parameters will change. How you are selecting your image. Now the clustering algorithm design a selection. So it depends on we obviously we have control over the algorithm. As per we will start, it is an iterative process, and we will make some clusters, then we will do the validation, we will check the result or accuracy. If it is acceptable, then okay. If it is not, we will then again go back to, again we'll change some, we will improve our clustering algorithm, then again we will see clusters. So this is not always manual. We in coding we can do this, and we can set this, okay, you check for these many clusters and for these cases, then you take the consider the best accuracy. After validation with ground truth, take the best accuracy model algorithm, then go with that. Then further knowledge means it again connects you with the your task specific. Suppose you got your flooded data, but one flooded data, it is, I mean, suppose you are using also getting help from digital elevation model. You are superimposing your flood pixels with the digital elevation model, and there it says that in digital elevation model it is some very high in altitude, high area, altitude area, there it is flooded. So you should cross check, you should not blindly believe on your clustering algorithm, you should recheck. That can be flooded, but that is not always, that is very much unlikely to get flooded. Okay, so there comes the other knowledge, and to decide which are flooded or not, or your work is your algorithm is working properly or not. So the feature selection relates to distinguishing features from a set of candidates, while feature extraction utilizes some transformations to generate useful and novel feature from the original ones. Both are crucial to the effectiveness of clustering applications. Proper selection of features can greatly decrease the workload and simplify the subsequent design process. Generally, ideal features should be of use in distinguishing pattern belonging to different clusters which are immune to noise, easy to extract and interpret. So, feature extraction, feature selection, you selected suppose an image, and suppose one flooded image, there you will look for how many clusters or how many classes. Here by cluster you can visualize, or you can call it as classes also. So we will, based on our knowledge, and we will try to decide on how many, roughly how many clusters are there. Clusters can be there based on the land use, land cover, based on other, as I said, based on other some parameters. Then suppose there can be so many types of flood. Suppose one river got flooded, some agriculture plots got flooded, some roads got flooded, some buildings got flooded, all will be different, and so we will get different these many separate classes. So it depends on your image that okay, these many cases are there, so these many clusters you want. Based on that, it is always preferable to set or decide some larger number of classes or clusters, so that you will not miss. As I said, you should not miss any classes. You start in broader way, then go in smaller scale. So start in larger scale, then you decide you iterative process, and you decide on, okay, final your classified map. So clustering algorithm design or selection. This step is crucial in clustering as it is related to the selection of a proximity measure and the construction of a criterion function. So proximity measure, it depends, proximity, it relates to some distance. Okay, the meaning relates to some distance. By that you can understand that it is up to you now, that okay, you know that you have to decide, or you should get some idea that suppose one area, it is 100 kilometers from the river that gets flooded, it if it can be flooded or not, and another area, it is suppose 10 meter from the river. Obviously the proximity is more, that 10-meter pixel, it is more probable to get flooded. Okay, by that you have to decide on certain parameters based on which you have, I mean, the algorithm in the model will decide some clusters. The construction of a criterion function. So now some function it will run, and how the some variables of that function you have to control. Now patterns are grouped into clusters according to whether they resemble each other. Thus the proximity measure will directly affect the formation of the resulting clusters. Generally, all clustering algorithms are explicitly or implicitly connected to some definition of a proximity measure. So proximity measure, it is also, suppose it is a distance measure. Many check for the direct angular distance. Many check for the some other type of distance, mathematical distance, or many Euclidean distance. So these many things come. Once a proximity measure is chosen, the construction of a clustering criterion function makes the partition of clusters an optimization problem. So it should be optimized, because you can't just give okay 30 numbers of clusters classes. It should be balanced based on the parameters. So clustering is ubiquitous, and a wealth of clustering algorithms has been developed to solve different problems in specific fields. However, there is no clustering algorithm that can be universally used to solve all problems. Greenberg states that it is extremely difficult to develop a unified framework for reasoning to diverse approaches to clustering. Definitely, it always depends on your image, on your data. So therefore, it is important to carefully investigate the characteristics of the problem at hand in order to select or design an appropriate clustering strategy. Now cluster validation. For any given dataset, clustering algorithm can always generate a division no matter whether a structure exists or not. Moreover, different approaches usually lead to different clusters, and even for the same algorithm with different parameter identification or the order of input may affect the final result. So, as I said, if you are changing the parameters of the algorithm, cluster algorithm, definitely you will get different output of your same image. So, you have to optimize your result. You have to get the best validated result. Therefore, effective criteria is important to provide the users with a degree of confidence for the clustering results derived from the used algorithm. These assessments should be objective and have no presence to any algorithm. Further, it should be able to answer questions like how many clusters are there in the data, the worthiness of the clusters obtained, or selection of an algorithm over the others. Generally, there are three categories for testing criteria: external indices, internal indices, and relative indices. These are defined on three types of clustering structure known as partitional, hierarchical, and individual clusters. So, And last, the result interpretation. So the ultimate goal of clustering is to provide the user with meaningful insights from the original data so that they can effectively solve the problems encountered. Experts in the relevant field interpret the data partition. Further analysis, even experiments may be required to guarantee the reliability of extracted knowledge. So now you got clusters. It is not giving you classes. So you got clusters. Now based on the experienced analyst, you will decide which cluster to call it a class. Okay, and which clusters to keep, which clusters to discard, which clusters to merge. Okay, it depends on the final classification. It depends on the analyst based on the experience, that it will decide, okay, I got 20 clusters, but now based on the other parameters, suppose for flood detection, as I said, based on DEM you can check based on the distance from nearby water bodies, or so many factors are there. So based on those you can check and you can decide and final that okay, these many you got these many as clusters. So it may be observed that the flow chart also includes a feedback pathway. As I wrote, that it is not a one-way process. Okay, you validated the result, you got, but you have to check and go back again to the first step. So cluster analysis is not a one-way process. It may, in many circumstances, it needs a series of iterative process. Moreover, there are no universal and effective criteria to guide the selection of features and clustering schemes. Validation criteria provide some insights on the quality of clustering solutions. However, to choose the appropriate criterion is still a problem requiring more efforts. So, it is not a one-way process. Obviously, in mathematical, the basics of clustering, I will discuss today the ISO data clustering, that is the first one. But nowadays the clustering, machine learning clustering, very famous in hydrological and SAR this domain. So there the machine learning approach, what it does, how it works in the iterative process, it will first process once, then it will learn, it will get some input from its first process, then it will improve its second approach or second data, depends, then again it will go back, again it will process, but this time with improved improved criteria. Okay, then third, fourth, depends on till it reaches its acceptable model. That also we will decide that when to accept a model or not. So steps in cluster analysis: data to cluster, data acquisition from satellite, preparation, pre-processing, and cleaning. Cleaning means again the noise, the speckle, all those things, as much as you can. Variables to use: selection of relevant variable for performing the clustering procedure. Irrelevant or masking variables should be excluded as far as possible. A proximity measure: designing a proper proximity measure. The clustering procedure: the number of clusters, even no cluster is a possible outcome. And replication and testing and interpretation. Clustering methods can be divided into two groups: partitioning and hierarchical approach. Partitioning approach aims to divide the dataset into several clusters which may not overlap with each other but together cover the whole data space. A data item is assigned to the closest cluster based on the type of proximity or dissimilarity measure. And hierarchical approach, it decomposes the dataset with a sequence of nested partitions from fine to coarse resolution, and it can be presented with dendrograms which consist of layers of nodes, each representing a cluster. This type of clustering is best represented by a dendrogram, which is a tree that splits the data space recursively into small subsets. The simplest approach for hierarchical clustering is to form each individual data point and then recursively merge two closest points, which may be based on a type of distance measure, into a subset until the whole dataset is in one cluster. So first approach is you are seeing the image or data space as a whole, and based on some mathematical sum, you are dividing the whole data space into certain clusters at a time. But hierarchical approach, it can say it is a tree like approach. You are growing your tree, or you are deciding, starting from very minute scale, then growing, so that you can, there cannot be, the error, it will not grow. Okay, you are starting from very little, and then you are checking, okay, this is qualifying the condition, this is qualifying the condition, this is based on both working similar or same, the proximity, this criteria. But this hierarchical approach is preferred over the at a time, because of it's a lot better, more accurate compared to the partitioning approach. So this type of, it is called, dendrograms or tree based method. So partitioning clustering, it there is the distance based, that k means model based and density based. So these many models. And hierarchical clustering, distance based, these model based and density based. So these are the some of the methods. So clustering algorithms used for the unsupervised classification of remotely sensed data generally vary according to the efficiency with which the clustering takes place. A conceptually simple but not necessarily efficient clustering algorithm which demonstrates the fundamental logic of unsupervised classification known as cluster. The algorithm operates in two pass mode, that is going and back, forward and backward. In the first pass, the algorithm sequentially builds class clusters. In the second pass, a minimum distance classifier is applied to the whole data set on a pixel by pixel basis, where each pixel is assigned to one of the mean vectors created in pass 1. So during the first pass, the analyst may be required to supply 4 types of information. As I said, that you have control over your algorithm based on which you want to cluster, because there it is task specific. In one area, the flood might happen at 5-meter distance from the river, and another area might be happening at 100-meter distance from the river. So that there we need to control, we need that knowledge, we need that data or information to further put into our algorithm. So R radius of the cluster, C a distance parameter for merging clusters, N the number of pixels to be evaluated between each merging of clusters, and C max the maximum number of clusters to be identified by the algorithm. All those. So to start the process of building of cluster centers, the first pixel of the image is considered to be the cluster center of the first class. You have to start any point. So it is considered as the center of the first class. Then the second pixel is taken up and its membership for the first cluster is found by computing the distance between the point and the cluster center of class 1. And so on. If the distance between the pixel and the cluster center of class 1 is less than or equal to r, the distance that we give, then this pixel belongs to class 1. And also, as I said, this distance is not always, it is not likely to always the distance, the physical distance we understand, suppose by meters, kilometers. It can be a mathematical distance also. Then Now the class 1 has 2 points within its cluster, and the cluster center of class 1 is modified by taking the average value of both the pixels. So now from which point is started, that changed, because then 1 point you have, now you found another 1 point of cluster. Now you got 2 points, and now your position of your point will change based on these 2 points, and then it will search for the third point, and then also the position. So you can visualize it is a growing approach. It is growing from 1 to 2 to 3, and that way it is covering, or it is deciding the pixels of classes or clusters. So like this, because these are the pixels of image, and these are the different points. Suppose here like, and you decide sum of the distance, and for now from this point and this point, it is this distance, this radius r. Then suppose you fix the r value of 15, and after the first iteration it will create this radius, and then it will take this point as that belongs to this cluster 1. Then the point shifted here, then again it will decide on other points. So now the third pixel is taken up for examination. If the distance between this pixel and the cluster center of class 1 less than or equal to r, then the pixel belongs to class 1. Now adjust the cluster center of class 1 by taking the average values of all the 3 pixels. If the distance of the third pixel exceeds the distance r, then this pixel does not belong to the class 1. Hence this pixel now becomes the cluster center of a new class, that is class 2. So if it qualifies, then okay, it belongs to the class 1. If not, then it will form another class. Like this. So it is outside the radius, the pixel 3. It does not come into the radius we gave. So now it will not be in cluster 1, it will be in clusters 2. So that way it will grow and grow. So this process of building cluster continues till n pixels have been examined. That also we will decide for their membership to cluster of different classes. At this point, the cluster building process stops temporarily, and the distance between class clusters are examined for their separability. The class clusters that have now been identified have to be checked such that the cluster centers of all classes are separated by minimum value c. So those clusters which are lying at a distance less than c have to be merged together as they belong to the same cluster. So now we suppose based on the r value distance, the first distance, we decided some clusters. Then again we want to check, okay, these many clusters are they enough discriminative, or they are enough different to each other, and if different or not, that is also that we will decide by the value of c. If they are lying at a distance less than c, then the same logic, we will merge the clusters. So these cluster algorithm, it is distance based, but obviously we can manipulate based on our requirement. If we want to check that as distance or not, we can check take that as some other parameters also. The new cluster center of the merged cluster are found by taking weighted average value of the old cluster centers being merged. So once the cluster centers have been checked for proper separability, so we found now the separability, are they enough separate? The building of cluster starts from the point where it had stopped. So it will it will build some clusters and using all the ensamples. Then it will stop. It will check, are they separated? Are they enough discriminative to each other? If okay, then okay. Otherwise, it will merge few clusters. Then again, it will go on. It is found that the centers of the cluster which have been identified tends to move in its position in the initial phase, and as more points are examined, the positions of the clusters start to stabilize before converging into a fixed position. So this process of cluster building continues till the maximum number of cluster centers have been identified or the end of image is encountered. So that this we will give that how many cluster centers to identify, and this is very important, very crucial information to give the algorithm, and it based on our experience and based on our knowledge about the data and the area. Okay, so finally the separability of each cluster is checked before proceeding to pass to this. So we decide on the points. Okay, so cluster 1 began from this point, but it grow, then it ended somewhere here. Similar, cluster 2 began like that and ended. Now pass 2. Having identified the cluster centers of all the classes, the classification of the image starts. So each point is assigned a class membership on the basis of minimum distance to means classifier. So they said the distance. It takes the minimum distance to means. When the whole image has been classified, the analyst now examines the classified image. Since the classes that have been identified are basically spectral class and not informational classes, hence the analyst now has to undertake the process of converting the spectral classes into informational classes. That means, suppose you are doing some clustering and SAR data for flood pixel mapping detection. Then you do all the process and you got 5 clusters final, but you don't know what are those clusters. Okay, those clusters you can tell those clusters are flood, but they are distinct from each other. So in which way they are distinct, you have to find out. Suppose you find out that okay, one depicts the flood in the forest, another depicts the flood in the urban area, like that. So you got some clusters, but to decide that into classes, you need or informational classes, that means something. You need that is the analyst work, and that is the final work. You have to decide on the classes. But in supervised classification, we already giving or telling or giving instruction to the model that only look for these classes only, and they are the classes. They have the informational properties. It will decide on the information. It will give you direct the class. It will not give you okay certain clusters or certain values, and you have to decide. There it will decide based on the training samples, but here you have to decide yourself at which one as class. So in this process of convergence, it is found that 2 or more spectral classes may combine together to yield a single information class, as I said. This process is rather a tedious, cumbersome and complex, hence requires a great amount of expertise on the part of the analyst in merging many spectral classes into one informational classes. Obviously, that depends on the expertise, but nowadays, as I said, it is proven, the clustering process, it is proven, and many are preferring this process in flood detection or in hydrology in SAR data, because I mean there the cost of missing any flood pixel is very high in real world also and in terms of image processing also. So no one wants to miss a class pixel. So better you get all the data, and you after that, based on some other parameters, many other parameters, you decide further which are what classes. So that is uh, preferable. So isodata clustering, this is the first very basic clustering process, iterative self-organizing data analysis technique. The isolated algorithm is similar in principle to the k-means procedure in the sense that the cluster centers are iteratively determined sample means. As we already saw that how the center is moving. The k-means procedure is based on the minimization of performance index, which is defined as the sum of the squared distances from all the points in a cluster domain to the cluster center. So as input to the algorithm isodata, the analyst has to specify a set of n initial cluster centers. This set, which need not necessarily be equal in number to the desired cluster centers, can be found by selecting samples from given set of data. For a set of n samples, isodata consists of the following principal steps. K is the number of cluster centers desired. Sigma is a parameter against which the number of in a cluster domain is compared. Standard deviation parameter, lumping parameter, and maximum number. So these are the your control. You can change as per your focus. I'm not going into very into mathematics based on these. And these are important when you want to do the clustering in coding. There you have full control over the equations. And in the last class I already showed you the application of k-means clustering. So today I just in detail covered the unsupervised classification, and already I showed in the last class, and later on I will show in hands-on if it is needed. So these are the some of the hands-on in Snap, because you have to always do this procedure whenever you are doing. So we saw these are the pre-processing of central one data. We already saw these lines and what are these. So now move to the we will move to the second topic of today's lecture, and that is that I will start today. It will not be finished. One, I completed the unsupervised, supervised, unsupervised classification basics, and those one thing to say, those basics, but in hydrological application, microwave and hydrology, those classifications, those methods are proven to work a lot better with least effort and least resources also. Many times people have so much resources, still they are preferring this clustering approach because, as I said, the reasons. So the second part that I will cover this part a little bit detail in coming weeks also. That's why I started this today, little bit of. And when comes the SAR, and it's in hydrological application, it is not directly related, but it is definitely, you can see it as a side product. This INSAR, you can say, there is this INSAR, there are this POLSAR, INSAR, these terms often you can heard. So this interferometry is another physical entity we can get from the signal, SAR signal. And what to get and what to do with that, we will see in further classes, also with applications, with hands-on application also. So one thing, the geometry and the theory first to know, and without the geometry, it is a simple geometry, simple theory. But without that, you will not able to visualize what is really happening when you will be processing. So it is a totally new term. So our objectives will be today to understand the principles of interferometry and understand the requirements needed for interferometry and get an idea about the application areas. So SAR interferometry. SAR is the synthetic aperture radar. Interferometry is a technique that uses two SAR antennas. Okay. So allows to get three-dimensional information from image pair covering same area. So till now we have saw that, okay, we are dealing with image that one satellite is taking acquisition of the data, and we got the data, we form some image and this. But this interferometry comes when two SAR satellites from two different positions taking image of the same area. Then only we will get this entity. So two SAR antennas and from two different positions. But there should be some that further we'll see. So synthetic aperture radar interferometry, in short INSAR, is a tool for measuring topography of the terrain, surface change and surface deformation. So it is very much popular to map the surface deformation. Depends on many reasons. Anything can be the reason, but this deformation, or in more detail to say, the land subsidence, surface deformation, land subsidence, these things. So the principle is interference of phase of two or more SAR acquisitions over the same area. So it is something about the phase. It measures phase difference and translate to path difference between different SAR acquisitions and obtain topographic relief or surface deformation from path difference, providing necessary parameter, that is spatial baseline, radar wavelength. This. So it is measuring, it is a measure of this. You are getting these two signals. Now you are getting the two wave, sinusoidal wave, and there the phase you already know, and that phase difference we are measuring. And why measuring that signal phase difference or wave phase difference, we are somehow geometrically, we'll see that, getting some idea, some height in z axis. Some, that is the way we, it has the application of, suppose your land is uplifting or downlifting, getting, that means going upward or downward, or any, in x direction also any displacement. So in any direction, any displacement, both x, y, z, it can monitor. And by using this process, the very popular and many DM generation are happening. And why this is so preferable, you can see in terms of cost itself. SAR is very much costly, SAR satellite, and get the signal, and then again the two, in the pair of signals, a pair of antennas. But still you can see the, as per the cost, the LiDAR, that is the light detection and ranging, and so there it lies in this price range. Okay, and it here the vertical accuracy in meter RMS. So vertical accuracy also, it says the more the vertical the accuracy, but the price also that much high with LiDAR sensor. And with airborne, this sensor, it is somewhere there. Spot satellite, that is also commercial, it lies somewhere here. But in satellite stereo pair SAR, stereo means the two looking at one, that is the stereo. We call it stereo pair when the two image from two different position looking at one image. So you can see the cost line here, and also the airborne stereo star also. Airborne SAR also giving you the DM, but not that much spatial coverage. Okay, the spatial coverage it is not given here, but spatial coverage is lot more in satellite SAR compared to airborne SAR. So comparison of airborne and spaceborne DM. So a DM of 2 km by 2 km derived from these areas, and the second one. So you can see the airborne and spaceborne, the accuracy also. So this is the one of the major applications to DM formation. Now methods, we will see how this is getting the height. So methods for interferometric SAR. So this is single pass. This is called single pass. This is the path. This line, this is the antenna, one satellite, and these two are antenna. Okay, so it is single pass. These two, from two antenna, it is looking at one point. Single pass. Here it is repeat pass, means it is going from here looking there, and again going from, coming back from here, when coming back looking at the same point. Okay, so from two different, this B, this is the baseline. Okay, baseline distance it is called. So it is the repeat pass. So this is how it works. The same for this, it is this one from two antenna looking at one position, but here it is the different baseline, and there looking at pass. So this is we call differential interferometry. DINSAR. Okay, it has the different baseline. Baseline limits. For spaceborne insert system, the baseline is typically on the order of 100 meter, though it can be as large as 1 or 2 kilometer, while the altitude ranges from approximately 250 kilometer for the space shuttle to 800 kilometer. That means the height. For low Earth orbit satellites, on the order of 2500 to 7000. So the baseline limit, when this is important, when suppose you are downloading the Sentinel-1 data, pair of data for interferogram generation, that time you have to keep in mind that which baseline till which you can go, you can take. So there it is less than 100 meter reduces the sensitivity to surface height differences, and greater than 2000 meter causes baseline decorrelation. For airborne insert systems, the flying height is usually of the order of 2 to 20 km, but the baseline is typically ranges from a few meters to a foot. So that again, R by B is the order of several thousand. R by B may range by this baseline, several thousand. Airborne sensor baseline is fixed in case of single pass interferometry. So conventional one antennas are, this is the one antennas are, return could be from anywhere on this circle. And how we till now we were dealing, or we are seeing only this type of thing. But now comes that this the same thing but two numbers. But it should be, the baseline should be here. Okay. So what happens when from two different positions we are seeing here? So return comes from intersection. So this intersection is important. We'll see. So basically this you can visualize the phase here. This is the signal. Suppose the green one, it is hitting the green signal, and for the red one getting. So these two are now two different wave, and their phase difference, I mean, if you visualize the shifting phase, the signal, the sinusoidal curve, it will be shifted. So there will be the phase difference, and because of the height, it is hitting a different point from two different. We'll see that in mathematically. So coherent energy, this is the, so coherent incoherent, we also see that this is the wave, the 2 points, this is how the wave further propagates, and this screening, I mean coherent and incoherent, if you visualize, go back to the first when we studied about the wave principle and signal, all those. So now what happens when these signals from these two antennas, they march further? So this portion, it creates this impression, this kind of impression. Okay, something there, if it gets the height, something is there. So it is, sir, we know already, we have seen that it is a complex image. It has the amplitude and phase part. Amplitude represents the ground reflectivity, speckle is there, phase, sum of two contribution, the sigma internal and sigma travel. Sigma internal is phase signature of the pixel internal contribution. Okay, Sigma travel is round trip travel time of the radar signal. So this is how it is getting the height. So in geometrically, S1 and S2, two are at different. Then the baseline here, and it is looking there. So these two signals it is getting when it is taking just the phase difference. Okay, so basically the internal and the distance. The first one, the difference of with the second one, and if we take calculate the mathematically, that in later class I'll show in detail and mathematics, then we will get some of this type of form. So this form basically 2 minus rho 1, it is giving us this height. This you can imagine this as the rho 1 and rho 2. So this difference is height. So one thing to show you the some of the results, interferogram, how it looks. So this kind of patterns and these images you can look. So interferogram is an image representation by pixel phase difference between two SAR images, and it varies scale 0 to 1, violet to 1, very red. An interferogram may be displayed in black and white or color. Each fringe represents 2 pi phase difference. The fringes, these are the fringes, the pattern, the circular pattern, these are the fringes. So interferogram, one color cycle or fringe represents a wavelength. So one color, just told you the fringe, one color of fringe, the lines. Suppose you can say the circular lines, concentric lines, one fringe. So by counting all the color cycles, we know how many wavelengths fit inside room this height. So more the fringes, by thumb rule you can say that it is more height. Okay, because more the fringes it will accommodate in, this is the height. Okay, the phase difference, the height. So more the fringes it will be, it will show in this portion, that means it has the more height. So interferogram versus local topography, you can see this is the interferogram was this portion, it has this height difference. If you generate this, this is how it will look. These does not have fringes, so it is of similar, not that much height difference. But this type of fringes occur when the height difference are there. So one thing to understand, many times people consider this as contours. Interferogram fringes do not depict the shape of contours. It is not the contour. Contour, if you create contour, it will be like this. There will be some elliptical center portion, then around that way the contour. But interferogram is not that. There is not any center you can see. So how does it work? Two images of the same area are required, measured from slightly different positions, A1 and A2. Due to the range difference, that is the rho minus rho dash, coming phases are out. This phase difference contain, so you can see this is the longer, this is the shorter. If you just divide, get the difference, then you will get the extra phase. This phase difference contain high information of the surface point and are used to create the interferograms. This is, now you can visualize these two signals are going and back from two different positions. We are taking the difference between these two signals of same point. So this is the range difference, you can tell it, or phase difference. So number of waves can be retrieved from the interferogram after phase unwrapping. There is one term to understand, phase unwrapping. Phase unwrapping means we are getting straight this sinusoidal curve, we will do make it straight, then we will take the difference. So there is one term is called phase unwrapping. We'll see in further in snap, we'll do those steps. So number of waves can be retrieved. So this is one wave, one cycle from the interferogram after phase unwrapping. So phase difference is the phi equal to rho, this range difference, to 2 pi by lambda into mod of 2 pi. So this is the equation from which we get the phase difference. This if you recall, the signals look like this, and the phase difference in number of waves, this is the difference. So phase image, recorded phase is the summation of the phases of all scattering elements within one resolution cell. About recorded phase, visual interpretation of phase images of one SAR image does not give any information. You already saw that is just a graining image, grayscale grain image. Phase differences between corresponding elements of two images can contain a pattern or fringe. So when we take the phase difference between two images, then only it gives you some meaning, and we get the fringes. This is the phase image. It looks like this. When we saw the amplitude image and intensity image, there we could at least make some pattern, but phase is nothing. Phase looks like this. That one single image, it is not any useful. Just to looking, it is useful, but by looking or in one single, we will not get any entity. By difference, you will get this. So these two image, and we will get this type of interferograms. So phase difference is important. Some basic flowchart using this or following this is to understand what to do. So dataset 1 and dataset 2, we said the two antenna data from two different positions. Image co-registration. We got two signal, but we have to co-register. We have to get one signal above another. We have to co-register. Then we will generate the interferogram. Then comes the phase unwrapping. So interferogram generation, we got the height, the phase difference, and the interferogram we got, but we have not got the height. Then we will unwrap the phase, we will make it straight, and then we will convert the phase to height now. So insert flowchart, The sensor data, SLC master image, it is always SLC data, single loop complex data that contains the phase. GRD data, using GRD data we can't, because GRD pre-processed data, the first level processed data, and there they processed, and it is not raw data, it is processed geocoded data. Now from two different sensor you got two term to understand: master image, slave image. It has different nomenclature. In India we call it master slave normally. So the master is the first one, slave is the second one. So it aligns the pixel in both image by co-registration. So register slave image to master image. The second one, that we call the slave image. The slave image is resampled to be perfectly co-registered to the master. Requires complex image resampling of the slave image. Co-registration must be within 1/4 of a pixel width. So these are some of the standards. Recalculate the amplitude and phases by interpolation. So again the same, how to compute the phase difference. Calibration, remove the flat phase. So calibration, we need to do this calibration to remove some flat phase. And output is the coherence image, complex interferogram. Now comes, today I will just go through overall one basics. You need to know the terms: coherence, interferogram, phase difference, these things. Now this coherence image comes. This coherence image, what does it mean? We saw the interferogram, okay, these are called the fringes. Each fringes are 2 pi phase difference. But now what coherence image? Coherence image, it gives you, suppose it has a scale from 0, that is darker, to brighter, to 1, suppose 0 to 1 scale. So higher the coherence means these bright pixels. And these bright pixels, using this you can understand, or you can it means that it is the highest correlation. Correlation in the sense, it is generated from two images. You can say two different images. So there, the brighter the pixel, lesser the change. So why to study the INSAR or coherence in hydrology? Because this coherence image has a lot of application in hydrology, microwave in hydrology. Okay. So here they are using the two images to get two images. Suppose one single date, two satellite image, and generate the coherence image to get the height. But we are not interested into the height. We are not doing into this land deformation and this subsidence. We are doing some hydrological, suppose flood detection, this works. So there this coherence image very much important, because if we visualize this way, if you get one data from before the flood and another data when flood happened, during the flood, then you calculate this. Now what I said, this brighter pixel, or the larger, the higher the value of the coherence image, more the correlated, and lower, lesser correlated. So that way, if you get the coherence image of pre-flood and during flood data, SAR data, you will get the change area. Change area in the sense, due to flood some things happen. What happens? The water comes on the land, the land changes, obviously it will not appear water, you can see water on the land. And also so many things, I mean, if some house gets destroyed, the damage due to flood and during flood, all those things as one change. So using coherence image, you can get the change. So there comes the application in hydrology of the coherence image, and it works very well. Just you have to consider the noise, the speckle of SAR. So we will see, and later on we will study in more detail, mostly focused on the coherence image, not in the height and interpret, because our task is different. Our task in hydrological application, we are not into detecting or calculating land subsidence. So how to calculate the coherence image, and we will see that how to detect damage, how to detect flood, all those things. So inside processing is subtract flat earth phase. So subtract the flat earth phase means we need the height. So it is subtracting the flat earth, the phase from the flat earth, by complex number multiplication for each pixel corrected phase equal to raw phase, flat, that is the flat earth phase, and corrected magnitude is the raw magnitude. Got this type of interferogram. And these are some of the output of the coherence map. Here is one satellite, here is two satellite. The values in a coherence map are an indication of the local differences between two radar images. Okay, as I said, it shows you the change, but not change, that is not the correct term, the correlation. So suppose these two area, if we see, some things changed here. So this is the darker, this one the change, because these are not that much correlated. The brighter, the more correlate. One house was there, here also that was there. So it is correlated, there is no change. But something was here, it is not there. Or something here changed. So that's why it is. So by mapping this change during flood, you can detect flood water. The coherence map these I will come in later. So the application, the DEM DTM generation, digital terror model. So there are the inside processing is very you can say the very error can happen. So many steps and so many things, and it is very data specific. It is not like okay, you are getting Sentinel-1 data and you just process. It is not that simple. You have to at each step. After each step, you have to look for the result, and if it is coming okay or not, you have to check and then proceed to next step. So error source, major error source happens or comes from the baseline accuracy, horizontal and vertical, that is the orbit's geometry. Low coherence, that is the phase correlation between the two SAR image, is the most important limitation and error source. Decorrelation and loss of coherence can be due to registration errors, spatial and spectral. the co-registration is not done properly. Temporal decorrelation, baseline decorrelation, orbit errors, inhomogeneous atmosphere. Decorrelation has a direct effect on the interferometric phase and thus on the height, and it happens. Among all those things, this baseline decorrelation, temporal decorrelation, okay, if you get some experience, you can handle this. There is no problem. Orbit errors. Registration errors come, depends on the which platform you are using, and depends on which method you are using. There are so many methods of, suppose, phase unwrapping. There are multiple methods. Which methods you are using, you have to understand, you have to know. So application areas, a lot of application areas, and INSAR is very popular nowadays. So digital elevation mapping, the first one, the slope map. So landslide hazards, landslide detection. Landslide means the land change, the land displacement, you can say. So it is useful there. DM generation, deformation mapping means the our Earth's surface due to many reasons. Due to, in suppose in recent paper comes in the Delhi flood, due to a Delhi flood, or is it happening, what reason? Because Delhi is sinking, many cities are sinking. Delhi is sinking at what level, at what centimeter level, sinking every year. So to find out those, and based on those to analyze further. And crustal motion monitoring, those things. Use of temporal coherence information, like us, that for our hydrological application, this temporal information, it is important for change detection, to find out the change. Now differential INSAR, as I said, the DINSAR, when one antenna, there is one satellite, but it has two antenna, it is looking at one image. So it uses at least 3 radar images of different dates to calculate 2 interferograms. Indicate changes in topography in 3 dimensions after subtraction of the 2 interferograms. Requires that the radar scattering elements did not change significantly. I will not go into detail to INSAR. INSAR processing I will show. So an earthquake, how, the fault zone and those, there the displacement in XYZ any direction you can get. So for today, till now I have covered the INSAR, some of the basics. I wanted to start it before, so that I can show you some hands-on application exercise of the INSAR, and also how to generate the coherence map, and from there what are the application or use in hydrology, because these are the latest technique. The latest technique in hydrology, microwave signal is in hydrology. These are the latest technique, and you can do small task in snap software. And so, but many theories to cover later on. Also in next class I will cover the important sum of theories in very detail, and then I will show some hands-on exercise. So if any question there, you can ask me in message. Any question or any doubt, you can mail me. For today, and if you need any material also, you can ask me. I can provide you for particular any topic. So for today, this is it, today's class. Next week we will see. Okay. Thank you.